Okay, so this question, we're going to integrate this complex function here, e to the z divided by z squared plus 3z, and it's on c. And c is defined here as modulus of z equals 1. So basically that's a simple closed contour. So that's what we know so far. So let's just draw that on the diagram here. So z equals 1. Let's turn that bit off there. All right, there we go. And that point there is 1. That's not perfect, but that's good enough now. We can see what's going on. That's a simple closed contour here. Now what we can do, we could integrate this function here without actually doing any integration at all by use of Cauchy's integral formula. So I'm going to write that down for you here. Cauchy's integral formula. Now, before we can go ahead on this one, there's a few conditions we need to start off with. First of all, the integral is on a simple closed contour. That's what that is. So that's simple and closed. We can see that. But we also need to be able to define that into a region, which is also a simply connected region. So we could define that inside here. That will be our simply connected region there. So we could call that region Z, where modulus of Z is less than 2. So it's not closed. So this one is an open one. So that's the region we can get our area C in. So that's good. That's the conditions of Cauchy's integral formula sorted. And we also need to assume, very importantly, that the contour goes this way, okay, rather than the other way. If you wait to the end of the video, I'll show you why that would be important. Okay, so now what we need to do, we can start attacking the function here. So e to the z, z squared plus 3z, we need to find the poles. So let's just rewrite this function, c, e to the z over, factor this out, pretty simple factoring, no problem. And now we can see where the zeros will be. So there's 1 at 0 and 1 at -3. So if we put them into the diagram here, got 0 here and -3 is here. So -3 is not inside our closed contour, so we're not going to even bother calculating that. If you just had this question on its own and these were our conditions, the answer would be 0. So if we just did this now, e to the z over z plus 3 dz, this would equal 0 because the -3 is not inside the contour. But we've got this function here, and our singularity here is at z equals 0. So poles at z equals 0 and -3. So this is the one that we're interested in. So what we need to do now, all we do is take this out of this function. So we let f of z equal e to the z over z plus 3. Take this one out and we're left with f of z equals e to the z over z plus 3. Make sure that's clearly a z. That's our function left without the singularity, because the function is not analytic at z equals 0. So now what we do is calculate this function at 0 and multiply by 2 pi I. So basically the answer is 2 pi I times f of 0, which equals 2 pi I times e to the 0 over 0 plus 3, which equals 2 pi I times, well, that's 1 over 3. So therefore the answer is 2 pi I over 3. And that's the answer to the question. Now what I mentioned at the beginning was, with the contour going anti-clockwise, if the contour was going clockwise, which is the opposite way normally in complex analysis, the answer would just be the minus of this, because you'd be going around this way. So now, so all you will get then is 2 pi I over 3 minus. That will be for clockwise rotation of the contour.